Okay, so here it is, the big video on how to do the Soundwave animation project that starts in Unit 2. You will notice that there is no page that says Soundwave animation project because it is comprised of all the data from all these different places, okay? And so I'm gonna walk you through this. While I do it live, I'm gonna pause and pick it up, but we're gonna walk through the whole thing. So the first thing though is to just get yourself set up in Desmos at the start, which is to go to, I'm gonna flip over to here. There we go. And then we're going to go up here. And I'm going to click on the, well, there we go, wrong tab. There we go. So you see this link right here? I want you to type that into Desmos. Okay, I'm going to even pause the video right now. Type it into Desmos. Sorry, not type it into Desmos. Type it into the browser. There we go. That's what I mean. That's your link to get to the Desmos template. Okay, I just pasted that in, I hit enter, and I have this. What you'll notice here, a couple things. Number one is that there's no plus C or plus D. C is having to do with phase shift, and the other one's having to do with midline, because when we were doing this sound creation, we didn't worry about those two aspects. Now, there is an opportunity for exceeding on the phase shift side, but doing a midline change doesn't really do anything for you unless the midline changes so fast that you're just literally adding another sound. And at that point, you're just adding another like sound to your thing. You're just doing it another way. So midline won't really come into play, but if you're doing exceeding, phase shift may, and we can look at that as well. And then you'll notice there's A sliders and B sliders. This is A controls the amplitude, B controls the period or the frequency of the note. And then down here you have your H slider, which right now is default at 50. Now, we're going to kind of work through all of this, but we're going to create something that animates in real time when we press play and makes it look like our waveform as we created it. A couple of things, we're going to change the amplitude. It's the VCA circuit that's going to change the amplitude. And the VCF circuit is going to change our filtering, so the amount of frequencies that get through, it's going to change our H value. Now, the actual way the circuit works is a little more complex than just changing this number. Actually, significantly more complex, but we're trying to model it closely conceptually and not perfectly, and that's okay. It'll look close enough. The ideas will all be there. Okay, you'd have to get into a much higher level of like college level stuff. I'm pushing you far enough. And then so that's the first thing. The next thing is that we need to have typed in our VCA and VCF equations. So here's my VCA equation. I'm going to put on screen just so, in case you haven't done it, for the sake of the video, I'm going to show you on my paper. Let me flip to that. There we go. On my paper here, this is on the whiteboard behind me, but I want to make sure this is in the video, and I will get my head off to the side. But here are all of the different equations. So if you're trying to find an RC value, if it says the attack circuit that's filling up, you just go negative. Don't forget the negative. It ends up just being a positive number, but this spits out a negative, so negative of that makes it positive. So negative attack time divided by natural log 1/3. And then if you're trying to do the decay or release RC values, that's negative. And then I just put T there because it could be the decay time, the release time, divided by a natural log of 0.05. Okay. But then once you have that, it's just a matter of like plugging in these values. So this is the attack equation, this is the decay sustain, this is the release, and these things in red are the things you're entering in. On the whiteboard, it's the things in blue, okay? Those are the things you're entering in. And all of that can be found in this, wait, I went way too far back. It's only 2 pages back. There we go, on this page here. And so all this information is here. Your RC values, if you calculated them, they're down below. Okay. The only thing that I need to take a moment for, because most of these things are you just find the box and you write it in. Where it says VN, the VN part comes, that's all different for each one. So if I want to know the VN for the attack on the VCA, I've written you a little equation for each one already. Okay, it's already written there for each one, and it's different and unique for each one based on how the circuit works. Okay. So I'm going to highlight that here as well. So there's my VN. That's where you get your VN. Otherwise, you're going to be looking at either your RC values down in these slots that you calculated or your data up here. Okay. So that's how you get to those equations. I'm going to pause it here, but I'm going to leave out this. And your objective right now is to go in and make sure that your equations match that pattern. Okay, match the pattern right here. Match this pattern. Okay. So I'm going to pause it here. I'm going to make sure mine match, and then I'll come around if you have questions. But you're trying to make sure that this matches your thing, including the hold time. Because when we did this in our first go around, we just put a hold time of 10 seconds for everybody, but we talked about it. You updated your hold time. It should update in your equation as well. Okay. All right. So this is where, this is not from like today's lesson. This is from previous lessons, but I was just reminding you. Also, if you wanted to stitch these together by limiting them, you can. We're going to actually do it another way here in a moment. But I want to just take this moment to remind you, if you're watching the video and those of you in the room, to make sure you share this graph, copy it, and upload it to the writing exponential equations assignment, because that's a separate grade from the project. So this assignment was a separate grade. We're going to use it in the project, but it's a separate grade. You need to upload this separately. Okay? If you don't upload this, then you get a 0 for the writing equations part. Okay? All right, now, I'm going to move forward. What we're going to do is we're going to flip over here to our document, and we're going to go back to our last page of the document, or last work where we did all of this attack, decay, sustain, release logic. So these are the equations that can turn on and off our different parts of the circuit, or different modeling equations for the circuit. They can turn them on and off, and our setup was just like this. So this was the logic for the attack time. What's in blue here would change on your document, but what's on purple is identical. But I also want to point out that the attack time, this one here and this one here, can and often is different for your VCA and VCF. They often have different attack times. Sometimes they can have the same one, but it's most often for them to not have different ones. But they always have the same hold time, because that's how long you held the button. When you let go of the button, both of them went into their release phases at the same moment. So these numbers better match. Okay? Okay, so that is a common error, to somehow get those confused and have one hold time for the other. No, they're the same hold time. Okay? All right, so once we have this data, here's all we're going to do with it. We're going to take this equation and multiply it by the attack equation on the VCA, and then take this equation and multiply it by the decay sustain equation. And by doing so, we're going to turn it on for only that moment and then turn it off. Okay? So what I'm going to do is I'm going to flip over back to here. And instead of this squiggly bracket thing here, you guys see this? Instead of that, I'm just going to go in and multiply by that logic. 0.5 parentheses 0.1 minus the, and this is where I'm using my attack time here. You have to use yours. 0.1 minus x plus 1. Okay. And when I do that, and I'm going to hide the VCF here, okay, I'll drag this up. Okay. Oh, sorry. I'm using the wrong letter. What letter do I need to use? T, because it's for time. On our document, on this document, we wrote X, but up here, the T is for time. So we've got to write T. Otherwise, the equation will not graph itself correctly. Okay. And then there we go. Oh, did I do this backwards? Am I not? Interesting. I will have to pause the video. Okay, I'm realizing where my error was, and it's something really dumb and simple. So you guys see here where I put absolute value of x around x? I don't know what I was thinking. It's absolute value around the entire top. This is what we did in Desmos, is we made it, remember how it was the absolute value of the whole thing? Do you see that? Yeah, then when I went down here, I just wrote it on, it should be absolute value of that whole top of that fraction. And that's on every one of these. And that is my fault, and I'm sorry. That's why I'm putting it in the video. I just made that error. That's why it wasn't turning out when I typed it in. Okay, so every one of these where their absolute value, it just needs to go across the entire top of that fraction. And I'm going to do that now. Okay, again, apologies for that error. I fixed it here on page. You can see all the things on top of this, the fractions, our absolute values are on the whole expression. So I'm going to go back over here, okay? And now when I type that in correctly, I want you to see what happens to the red graph. And to help you see it, I'm going to zoom in on the time parameter here. And I'm going to go to make it a little more obvious. Okay, here we go. All right, now, here's my attack graph. Do you see the red curve coming up, coming up, coming up, coming up? And then it stops, and what happens to the red curve? Yeah, and then it turns off. Do you see where it just turns to 0? Okay. Now notice that I didn't cut off this stuff before time 0. And that's because in our animation, we're going to have our animation start at time 0. We'll set that up later. So I don't need to worry about this part. I don't need to create some additional logic because my animation will start at time 0. Okay? So this equation is on, and then this logic will turn it off. And we're just going to do that same thing for all of these. But here's the catch, and I need you guys to see, look up here. Look up here. This is a common error. So on the decay sustain one, do you see this +2 right here? So if I just start by typing in plus times 0.25 and start doing the logic, all I'm multiplying is this 2. That's it. If I want to multiply the whole thing, I got to highlight the whole thing and put a parentheses around that. And then when I type in this whole logic, which is a whole long string, so value x minus 0.1 plus 1 parentheses division absolute value 10 minus x absolute value 10 minus x plus 1. Okay. Oh, I keep putting x. T. Sheesh. T. Because that's time. I keep copying it down for the sheet. And then now when I do that, do you see how I have this red graph is on, but the blue one's off at that moment? And then the blue one turns on that moment that the red one turns off. And then it carries over. Wow, I need to zoom out because this carries over for a while. And then the blue one turns off here where the green one on my screen, where my release one turns on. And so I just need to continue that process until I've done it for all 6 of them. Okay, all 6 of them need their logic added. Okay, go. I'm going to do that here, and then we're going to come around and help, but I'm going to pause the video now. Okay, now that you are here, or when you get here, where you have this whole thing stitched together, but stitched together not through little squiggly brackets, but through that absolute value logic. When you're there, you can then write a master equation. So what I'm going to do is I'm going to actually add it up to the top here. I'm going to write a little expression up to the top here. And all I'm going to do up here is I'm going to write v sub out, like I've been doing. And then I'm just going to copy what's after the equation here, paste it, and then go plus, and then copy what's after the equal sign here, and paste that at the end. And then I'm going to go plus. And I'm going to take the third phase, and I'm going to add it to the end. Copy that. Plus. So they're all 3 added together, and when I do that, and I turn off this one here, do you notice that the graph is all just one color now? It's one equation. Okay? It's one stitched together equation. Now there is one quirk with this logic, and it happens at the transition moment. So I'm going to zoom in here at 10 seconds. This is one of my transition moments. Okay, can you guys look at the screen? Does that look pretty close? If I zoom in far enough, there's always a gap because there's an estimated round off. Oh wait, sorry, I take that back. That gap would be here. Oh wow, man, did I really round precisely? Oh, mine won't zoom in anymore. If you get to the point where you don't see a gap at all, congratulations, you really didn't round. Or you let your hold time go plenty far. Sometimes you'll see a gap. Okay, almost always there is. And this one there didn't happen to be. Okay, anyway, but if I were to actually click on this dot, I want you to look on my screen. Look what happens at 10 seconds. What does it say? Undefined. And that's because right here in the logic, at 10 seconds, do you see right here? I have 0 divided by 0. And so the quirk is this equation works everywhere except the transition moments. There's like a brief moment where it flashes off. The whole equation goes away because it's undefined at that one dot. And so you'll notice when we actually do an animation and we press play, is there might be a frame that just misses. It like disappears for a frame, and that's okay. It'll only be for literally a frame, and sometimes it skips that frame and you don't see it. Okay. So anyway, there we go. Okay, and then you're going to do the same thing with the VCF. Okay. So I'm going to add an expression. Here, stick it there. Oops, no, I didn't want to stick it inside of that. There we go. And then I'm going to do the same thing here. I'm going to hide that one. Actually, sometimes it's good to just copy your attack wholesale, because that's where one you're starting with. And then copy this one and add it. Oh, I put the +1 on the wrong part of this logic. Okay, plus the next one, and then plus. I do have an error in this one that I'm going to have to fix, and I'll show you that. Okay, here in a second. I do have this. This is one error, clear error. Okay. All right, and now I'll stick that as well. I am going to show you, I did have an error here, and I noticed, did I already fix it? I did. Okay. Oh, I just had an error here, but that didn't matter. So anyway, I stitch those together, and then it lines up. So that's our next thing, is to stitch them together by adding them so that they're one solid equation. Pause the video now. The next thing we're going to do actually is change this V out here so that we know where to put it, because we're going to go copy it and paste it into our animation. So the VCA affects the amplitude. Which letter on this graph is amplitude? A, B, or H? A. So what I'm going to do here, just to help remind you, I'm going to change this to just say A equals. Okay? And then the VCF affected the H, the frequency response. Okay? And so those are the first two things I'm going to do here, is I'm going to copy this in, and I'm going to paste that in for my A. Okay? And then I'm going to copy this one in and paste this one in for my H. And then what you'll notice, if you look on my screen right now, it tells me to add a slider, but what's the slider for? For time, because now that's how we're going to animate. We're going to animate over time. And so I'm going to do this in the video, but I'll help you. You can click this slider, but here's the thing. I usually like to drag it to the top so that when I know the top button is click play. But then you have to see this on screen. It's not going to make any sense if you don't look at it on screen. I'm going to hide my other waveforms here for a moment. Okay. If I click here where it says animation properties, this is where I can change the speed, but I can also change how it goes. Do you see how this one animates back and forth? Is that how a sound goes? It plays forward and then plays backwards? No, so I'm going to animate forward, so it keeps playing that sound and cycling. And then how long where it needs to start down here at the slider, I want the slider to start at 0 seconds when I press the button. And then it needs to last long enough for it to go through the whole cycle and process. I'm holding the button for 10 seconds, so I need to give it even more time to like decay out or after the release phase. So I'm going to put like 15. You'll have to adjust this. And then if I do hit play here, okay. And so its amplitude is changing pretty quickly because I have some pretty quick attack time on there. And then you can see it's filtering out. We've got more revisions and refinements to do to this equation, but there's only one other sort of bedrock thing I need to do. So I'm going to pause the video, give you a moment to catch up to where I'm at. And then there's one other bedrock thing to do before we get into sort of the nuances of details. There is one more thing we have to do. Well, there's two more things we have to do for meeting, but one's pretty simple and then the other's a little more complex. Okay, this is a lot where we're going to end with the meeting, and I'm going to show you the remainder of the process. But some of this you can't fully do without having your sound or a video of your sound there beside you. Okay, Travis, I need you to focus. Thank you. Okay, so the first thing that I'm going to show you is pretty simple, and that is you need to have your B match the frequency of your wave. Okay, so this B value, rather than actually typing in the B value, we're going to type in the formula. So I want you to go in right now, get into the B value, and type the number 2, and then the letters PI for pi, and then multiply it by the frequency you wrote down on this sheet of paper. So there's a box that says frequency. Mine was 87 hertz, so there we go. And then divide that whole thing by 343, which is the speed of sound. Okay? And when you do that, this is now physically modeling the size of your wave in meters. This is the actual distance of your wave in meters. Okay? So again, that's 2 pi times the frequency divided by 343. Okay? Pi is all you need for pi. Okay? So that's step number 1. Okay? I'm going to pause for a second. The next thing is don't delete, because there might be an exceeding opportunity to blend some sounds together. Don't delete the wave that you don't need. Just hide the ones so if you're a square wave, you would hide these two, and you have a square wave. So I'm doing a sawtooth for my example, so I'm going to hide the others. Just hide them. And here's the real, one of the big quirks. You're not going to have to type a ton in, but you are going to have to do something a little funky. Ready? So this right here, if we look at this, does this ever become a perfect sawtooth? No, but in the actual circuit, it got pretty close. And the reason why it doesn't get there is because this model, while it does follow a voltage, this is the voltage doesn't perfectly correspond with the actual frequency of the filter. It's not a one-to-one relationship. In fact, it's typically an exponential relationship. And so what you're going to do to fix that is I'm going to go in here for my H. I'm going to cut out the entire expression. I'm going to go cut. And then I'm just going to write F to the power of, and then paste that whole thing back in. And then now, do you see where there's a slider to add? Okay, this is like the frequency knob on my thing, and you are going to want a number between, it can't be 1 because nothing will happen, but it has to be between 1 and 2. And you can just use a slider to kind of experiment. Somewhere in here is probably going to be your sweet spot. Okay, and we'll tune this more later, but if I do this, do you see how this, now if I have this up here, do you see how that's getting more to an actual sawtooth wave? Okay. And so I'll tune it later. That'll be a Thursday practice, but you just need to set that up. F to the power of that whole equation. because the circuit isn't just a voltage directly translating to a frequency. It's something more complex than that, exponential. So f to the power of. And then the very last thing that I'm going to have you do, and all I need you to do is to just type this in here. I'm going to zoom in. So find your thing that you're working with right now, and this is what you're going to type in. You're going to type in plus R times R divided by N times the sine of, what are we trying to say? Shoot, actually, we're going to have to get to this later. I'm just going to add this to the next video. We don't have time. It's about resonance. It is part of meeting, but we don't have time. I'll have to add it to the next video.